The last property of waves that I want to introduce you to has to do with the orientation of waves in space. Consider this slinky. If I pluck it like this, I can create a compressional wave in it. Compressional waves are also called longitudinal waves. In this type of wave, the medium shakes back and forth as the energy passes through the medium. The amplitude of the wave is parallel to the velocity of the wave. If I shake the slinky like this, I can create a transverse wave instead. In a transverse wave, the medium shakes up and down or side to side as the energy passes through the medium. The amplitude is perpendicular to the velocity of the wave. We can use this information to distinguish between longitudinal and transverse waves. Let's say this slinky represents a longitudinal wave. If I rotate this slinky, you cannot tell that I rotated it. It looks the same. That's because this type of wave has so much symmetry to it. Let's say this bent wire represents a transverse wave. If I rotate the wire, it does look different. In this orientation, it is clearly vibrating up and down, and in this orientation, it is clearly vibrating side to side. It turns out that there is no real preferred orientation of vibrations in most natural light sources. If you look at the light coming out of a bulb, or a candle, or a star, any given bit of light could be vibrating in any orientation. Each orientation is equally likely. Instead of worrying about all the different orientations, we can just assume that when observing a natural light source, 50% of the light is vibrating up and down, and 50% of the light is vibrating side to side. As we said, we can easily tell what the orientation of our wire model of a transverse wave is. If we can tell these conditions apart with our eyes, we should be able to build a tool to see the difference too. Here's a perfect tool for this job. It's just a slotted fence. If I hold the fence like this, light that's shaking up and down can go right through, but light that is shaking side to side cannot. This would allow half the light to get through. If I rotate the fence 90 degrees, it still lets 50% of the light through, but it's the other 50%. My fence is acting like a filter. I can select which orientation of light I want to pass through the filter. Let's suppose I have a couple of these things. What if I pass light from a random source through two filters? The first one blocks 50%. If I put a second one in the same orientation as the first one, it does not block any additional light. The pair together still block 50%. However, if one of the filters is in this orientation and the other filter is rotated 90 degrees relative to the first one, we now block 100% of the light. Okay. Yep. Some of you might be thinking, but when you use two filters, I could still see light coming through it. That's because my big wood fences are only meant to interact with my big wire wave. If we want to interact with real light, we need a much smaller fence. This sheet of material is called Polarizing Film. It was invented in Connecticut in 1909 by Edwin Land, who started the Polaroid Film Company. This material is a polymer. We talked about polymers during our momentum unit. Polymers are materials made of long chain molecules. In this case, each molecule contains thousands of carbon and hydrogen atoms. The chains line up parallel to each other, creating a really small picket fence, small enough to interact with visible light. Let's check it out. Here I have an old overhead projector. This is some quality 1970s technology, and it's useful for our purposes. I can use it to project a nice uniform area of light on my wall. It's evening and the lights are out, but this is as dark as my home office gets. Let's call this area white, meaning 100% of the projector light is hitting here, and we will call this area black, because 0% of the projector light is hitting here. If I put my hand on the projector, it makes a shadow on the wall. The shadow is the same color as the black area. Does that make sense? Okay, now I'm going to put a polarizing filter on the screen. You can see that right away there's a new color on the wall. I contend that this color, which I will call gray, is halfway between the white and the black colors. This is because I'm blocking 50% of the light with the filter. If I rotate the filter 90 degrees, the color does not change. I'm still blocking 50% of the light, even though it's a different 50%. If I add a second filter in the same orientation as the first, there's not any significant color change. I'm not blocking any more light. Watch carefully as I rotate the top filter relative to the bottom filter. The overlap area is turning more gray. At this point, the filters are 90 degrees apart and the overlap is black. See, it matches my shadow. We are blocking 100% of the light. If I keep rotating, we will come back to a situation where we are only blocking 50%. Let's look at some applications of this idea. Many of you probably already realize the most obvious application, sunglasses. The job of sunglasses is not to make you look cool, but it is to block 50% of the light from getting into your eyes. Here's an important question. What's the orientation of the filter effect in sunglasses? Like this? Like this? like this. Let's be more specific about the job that sunglasses are intended to perform. Sunglasses are primarily used to block glare from horizontal surfaces like pavement or car hoods or still water. The light that comes from a bulb is randomly oriented, and sunglasses will always block 50% of that stuff. Is the light that bounces off horizontal surfaces still random? No, it is not. If I throw a stone overhand into a pond, it goes right into the water. Kerplunk. If I throw it sidearm, I can get it to skip across the pond. The same is true with light. The vertically vibrating light that hits the water digs in and gets absorbed. The sideways vibrating light skims off the surface and comes toward you. To block this light, my glasses need filters in this orientation. This diagram shows that 50% of the light from the sun will get through your glasses, but almost 0% of the glare from the ground or water will get through your glasses. These images show the difference between what you see with or without sunglasses on. Here's another place where we find polarizing filters: calculator and clock screens. When you type something in your calculator, the numbers show up in black, but there's no such thing as black light. How does this happen? First of all, notice that the color of the screen is similar to the color of our filters. The screen is a filter that blocks half the light in the room from getting into the calculator. There is not just one filter though. These screens work because of an interesting three-layer cake of physics. The top layer is a Polaroid film that we have been talking about. The second layer is a different type of polymer. It's called a liquid crystal material. It is made of the long spaghetti strands of carbon and hydrogen, but instead of being lined up in nice straight rows, they are all jumbled up and do not act as a filter. However, if we electrocute these jumbled molecules, they will straighten right out, just like the hair of a kid touching a Van de Graaff generator. We can selectively electrocute each individual pixel on the screen in the second layer. The bottom layer of the physics cake is a mirror. Light from the room goes through the first layer, it goes through the second layer, it hits the mirror and bounces back up to your eye. If the screen is blank, the middle layer is not a filter, and the whole screen is the 50% gray color of the first filter. If we want a character to appear on the screen, we electrocute the pixels we need to create fence pickets perpendicular to the main screen. None of the room light that bounces off the mirror can get through these electrocuted parts of the screen, and the character appears black. Interestingly, the people who make calculators and clocks realize you might want to use your calculator with your sunglasses on, and they make sure that the top filter is in the same orientation as your glasses. That means you can still see the screen. However, if you cock your head to the side and look at your calculator, the screen will look completely blank. Here I have a roll of packing tape. I'm going to break a piece off and put it down on a sheet of polarizing film. If I look at the tape through another polarizer, we can see that the tape appears to change color. This has to do with the interaction of the light with the molecules of the tape. As the light passes through the molecules, some colors are polarized in one orientation and others in a different orientation. If I rotate the top filter, I can change the color that we see. The colors that we get depend on the thickness of the tape. If I add another layer of tape, we can see that each layer is a different color. If I rotate the filter, the color of each layer changes. Art students might notice a pattern in the color changes. A given layer's color changes to the complementary color when you rotate the filter 90 degrees. Here is a sheet protector covered in tape. The numbers drawn in Sharpie represent how many layers of tape there are in that section. We can see that we get different colors in the first several layers, and then the colors repeat with more layers. The tape from different companies is different in composition and thickness and produces different colors. I very often do a cool art project with students based on this idea. We have kids draw a simple picture and put it in a sheet protector. Then they cut out tape in the shapes of the objects they drew and build up layers of tape in each area that will become the color they want. When they're done, we can do things like this. This is a flower. This is a sailboat. For kids that don't have the patience or dexterity to make a specific picture, we let them cut random shapes and overlap them to create abstract art. Here is a protractor. It is made of a polymer material. If I put it in between our polarizing filters, we get some colors just like the tape. Areas that are different colors tell us about the quality of the plastic. The two interesting features that show up on the protractor are this line and this dot. Do you know how you make these things? They are made by a process called injection molding. You make a mold for the object and squirt hot liquid material into the mold with a needle. The dot that we see when we put the protractor between the filters is the spot where the needle got inserted into the mold. The pressure from the needle sends the material around the mold. The material meets up over here and form a joint. This is called a cold joint because the material was cooling as it squeezed through the mold. The line that we see when we put the protractor in between the filters is the cold joint. If you dig around through our drawer of protractors at school, you will find a lot of broken ones. Almost all of them are broken in the exact same place, on the cold joint. It is the weakest part of the object. We can use polarized light to see stress in the material. If I flex the protractor, you can see the colors change. This indicates that the material is being damaged. The more the color changes, the more stress there is. Before engineers build a new tower or bridge, they often make a scale model. This used to be done with wood. To see if a tower design was a good idea, you would make a model and then try to break the model by adding compressional forces to it. The problem with this is that the wood seemed fine right up until the point where it shatters into thousands of pieces. When it breaks, it's hard to do some forensic force calculations to figure out why it broke. While it is still common to build wood models in contests like Science Olympiad, professional engineers have not been using wood for the last 30 years. They use a polymer. They can build a scale model of their design and apply forces to the design while watching for color changes in the material. They never have to break the model. They can stop adding forces when they see a color change and then reinforce those areas if they think they need to before adding more force. The last application we will talk about is 3D movies. To make a 3D movie, you have to duplicate your experience of stereo vision with two-dimensional information. What I mean by that is this. Since your two eyes are spaced apart, you actually see every object in front of you from two perspectives, and your brain puts that information together to make things look 3D. If I film a movie scene with one camera, that same single perspective gets into both of our eyes when we watch it and we think the image is flat. To make a 3D movie, you actually film each scene with two cameras, each about as far apart as your two eyes. If you just watch both of them at the same time, you see a blurry movie because all the information is going to both eyes. The trick is to get the information recorded by the left camera to just go into your left eye, while the video recorded from the right camera just goes to your right eye. In the 1970s and 1980s, 3D movies were awful. They would record the right eye scene in red and the left eye scene in blue. If you wore the funny red and blue filter glasses, the scene would look 3D, but the coloration was not natural. Modern 3D movies are different. We still record each scene with two cameras, and we still play both scenes onto the screen at the same time. But the information for the left eye is polarized in one orientation, and the information for the other eye is in a different orientation. By wearing glasses with different fence orientations, you can get the correct information to the correct eye without any color distortion.